Here's the first lesson of the quadratics unit where I'm going to introduce you to quadratic relationships. In section 1 of this lesson, I'm going to start by comparing and contrasting linear relationships to quadratic relationships. And as a reminder, a linear relationship is a relationship between two variables where the rate of change is constant. This means that when one variable increases or decreases, the other one does so at a constant rate. And the graph of a linear relationship is always a straight line. And the simplest form of a linear relationship is the equation y equals x. Let's start by filling out this table of values for that relationship y equals x, and then calculate the first differences in the y values to reveal that constant rate of change. Now, to complete this table of values, I can just use this equation that tells me that y is equal to x. So all of these y values are exactly equal to these x values. And then to calculate the first finite differences, that just means to find the difference in consecutive y values. So looking at the first pair of y values, you do the bottom one minus the top one, -2 minus -3. That means -2 plus 3, which is 1. And then just repeat this process for each pair of y values. The next pair is -2 and -1. Doing the bottom one minus the top one, -1 minus -2, I again get 1. And if you repeat this process for each pair of consecutive y values, notice that all of the first differences are 1, which means there is a constant rate of change between the y values, which means this is a linear relationship. For all linear relationships, the first differences are constant. And that's why if I were to graph these points that make up this linear relationship, it will form a straight line. And now let's move on and look at a quadratic relationship. Now, a quadratic relationship does not have a constant rate of change, but its rate of change itself changes at a constant rate. The simplest form of a quadratic relationship is the equation y equals x squared. And any relationship between two variables can be represented in 3 different ways. So to fully understand the properties of a quadratic relationship, not only do we want to look at its equation, but we should also look at its table of values and its graph. So to complete the table of values, I need to calculate these y values by subbing all of these x values into my equation and calculating y. Right? This equation tells me that the y values are equal to the x values squared. So to get this first y value, I know y is equal to the x value squared. And -3 squared means -3 times -3, which is 9. And then -2 squared is 4, and so on. Square each of these x values, and I get their corresponding y values. And now I'll complete this column of first finite differences by finding the differences in consecutive y values. Looking at the first pair of y values, if I do the bottom minus the top, 4 minus 9 is -5. And then looking at the next pair of y values, bottom minus top is 1 minus 4. And that gives me -3. And then if I complete the rest of this column of first finite differences, I notice that these finite differences are not constant. They're not all the same number, which means these values are not changing at the same rate. There is not a constant rate of change for quadratic relationships, so their graph is not going to form a straight line. But if I calculate the second finite differences, by finding the differences in the first differences, looking at the first pair of first differences, doing bottom minus top, -3 minus -5, that's -3 plus 5, which is 2. Looking at the next pair, bottom minus top, -1 minus -3, that's 2 again. And if I complete the rest of this column, I see that the second differences are all the same number. The second differences are constant. That means for quadratic relationships, the rate of change is not constant, but the rate of change itself does change at a constant rate, and that's indicated by the second differences being constant. So at the bottom here, notice it says that the second column of finite differences is constant for quadratic relationships. And if I plot all of these points for this quadratic equation, I'll see that quadratic relationships are non-linear. They actually form this U shape called a parabola. And before moving on, a couple things I want to point out to you, that when we have a linear relationship, the highest exponent on the independent variable x is 1, and the column of first finite differences are going to be constant. And when you have a quadratic relationship, in the equation you'll recognize it because the highest exponent on an x is a 2. And for all quadratic relationships, the second column of finite differences are all constant. Now, they're not always all going to be 2. It's just they're all going to be the same value. They could all be 10s, for example. And now let's move on in the lesson where we summarize properties of quadratics. So the shape of the graph of a quadratic relationship, which I have 2 samples down below here, and here, that shape that it makes, we call that a parabola. And all parabolas have a maximum point or a minimum point called a vertex. Now, if a parabola opens up, like this parabola here on the left, if it opens up, the vertex is at the bottom of the parabola, so it's a minimum point. But like the parabola on the right side, if it opens down, then the vertex is at the top of the parabola, so it's a maximum point. And all parabolas are symmetrical. If you draw a vertical line through the vertex of the parabola is symmetrical on either side of that vertical line. And this vertical line that goes through the vertex of the parabola is called its axis of symmetry. Now let's go ahead and start doing a couple examples. In section 2, we're going to be working with quadratics that are given in standard form. So the standard form equation of a quadratic relationship looks like this. Y equals ax squared plus bx plus c, where a, b, and c are constants. They can be any real number, as long as a is not 0, because then that would make the equation linear. But notice in this equation, the highest exponent on our power of x is 2. That's what makes this a quadratic relationship. And the graph of any quadratic relationship is going to form a parabola. And I know if I were to calculate finite differences, the second column of finite differences would be constant. That's what we know about quadratic relationships so far. So let's practice working with a few quadratic equations that are in this standard form. First of which I see right here, y equals x squared plus 2x plus 1. Let's sketch a graph of it by completing the given table of values, and then state the vertex and the axis of symmetry. So in this table of values, I've picked the x values for you. Now to get the y values, we'll have to use this equation that tells us the relationship between the y and x values of all the points that make up the quadratic. The equation tells me that the y values are equal to x squared plus 2x plus 1. So I'll just take each of these x values and replace the x's in this equation to calculate y. So maybe I'll write out the first calculation for this first y value. I'll just sub this -4 in for these x's. And then simplifying that equation, y equals 16 minus 8 plus 1, which means the y value is equal to 9. So when x is -4, y is 9. And I could then do that same process for each of these x values to calculate their corresponding values of y. And now I'll plot each of these points. And by connecting these points, I'll see once again this U shape, which we call a parabola, that all quadratic relationships have. The question then says to state the vertex and the axis of symmetry. Well, since this parabola opens up, the vertex is its minimum point, this point right down here. So the vertex is at the point -1, 0, and the axis of symmetry is a vertical line that always goes through the vertex of this parabola. So the axis of symmetry would be the equation of that vertical line. To write the equation of a vertical line, it's always x equals the x-coordinate of all of the points along the line. Well, the x-coordinates of all of the points that make up this line, the x-coordinates are all -1. So the equation of that vertical line is x equals -1. And just for fun, if you wanted to, you could calculate the columns of finite differences. The first column of finite differences, notice the values are not constant, which is why this is not a linear relationship. But these values all change at a constant rate, which is why it forms this nonlinear U shape. So the second column of finite differences are always constant for quadratic relationships. So hopefully you're starting to see the properties of these quadratics, and you would be able to recognize a quadratic relationship from an equation by seeing the highest exponent on the power of x is 2, or from a graph by seeing that it makes this U shape called a parabola, or from a table of values by seeing that the second column of finite differences are constant. Now let's go ahead and do another example. But first, let me point out one key property of quadratics in standard form that you need to understand. In a standard form quadratic equation, the a value, the coefficient of the x squared, which we call the leading coefficient, tells you the direction of opening of the parabola. If the a value is greater than 0, so if it's positive, the parabola opens up. And a parabola opening up would look like this. And I'll put some plus signs here, make it look like a smiley face so that you remember if a is positive, the parabola opens up. But if a is less than 0, the parabola opens down. And a parabola opening down looks like this. And if a is less than 0, that means that it's negative. So I'll put some minus signs for the eyes on that frowny face. So maybe these diagrams will help you remember how the a value, if it's positive, it opens up, but if it's negative, it opens down. And one more point that I want you to learn here is that the y-intercept is at the point 0, c. So in the standard form quadratic, this c value always tells you the y-intercept. And why that is? Well, any point on the y-axis has an x-coordinate of 0. So if you set these x's to 0, that would eliminate these first two terms, giving you a y value of c. And let's use this information to complete example 2, which says state the direction of opening and the y-intercept of the given quadratic, then make a table of values and sketch the graph. So in part A, I see that this equation is for a quadratic relationship because the highest exponent on the x is 2. And since the leading coefficient, the coefficient of the x squared term is negative, I know that this parabola will open down. And the y-intercept is going to be the constant value of the quadratic equation. So for this equation, the constant value, the value at the end that doesn't have a variable, is 2. So the y-intercept will be at 2. And that could have been calculated just by subbing in 0 for x and calculating y. When subbing in 0 for x, that term will be gone, leaving you with y equals 2. And now I'm going to complete a table of values to verify those two properties we just wrote. I'll choose the x values for you, and then I'll explain to you after why I chose those x values. I'll choose x values between -3 and 3. And now to calculate the y values, I'll just take each of these x values and sub them into my quadratic equation for x. So to get my first y value, I'll just take -3 and sub it in for x to calculate y. And that would be -25. So the first y value is -25. And then I'll calculate the remaining y values using the equation as well. If I graph all of those points, I'll get my parabola shape. I was only able to fit 5 of the 7 points on my graph. This first point and last point didn't fit, but notice I have this parabola that has a y-intercept at 2, just like we said it would, and the parabola opens down. And also notice I put arrows on the ends of this function because quadratics do continue forever. And then I also said I would explain to you how I chose these x values. Well, notice this point 0, 2, if I look at the graph, that's the vertex. That's why I chose an x value of 0 to be in the middle of the table, because I knew that was the x value of the vertex. And then I chose some x values to the left and some x values to the right of the vertex. That way I made sure I got both sides of this parabola to get the u-shape. And now let's do part B. In part B, the coefficient of the x squared term, our a value, is 2. So since the a value is greater than 0, this parabola opens up. And the y-intercept is equal to the c value, which is the value of the constant term. So the y-intercept is at the point 0, 3. Now the x values I'm going to choose for this function, I know that the x-coordinate of the vertex is actually going to be at 2. You don't have to worry about how you get that yet. Like I said, you'll learn that later in the unit. But because I want to make sure I get points that form that u-shape, I'm going to choose points to the left of 2 and to the right of 2 so that I can get the parabola shape. And now I'll calculate all of the y values by taking these x values and subbing them into this equation for x. So let me do that with the vertex. Let me sub in 2 for these x's and calculate y. If I do 2 times 2 squared, well, that's 2 times 4, which is 8. Minus 16 is -8, plus 3 is -5. And then I'll do the same thing. I'll calculate the rest of the y values using this equation. And now I'll plot all of those points on the graph and verify that this parabola opens up and has a y-intercept of 3. And there's that parabola with a y-intercept of 3 that opens up. And even though the question doesn't ask, I think it might be useful for us to write the equation of the axis of symmetry for each of these. Let me start by drawing in the axis of symmetry for each of them by drawing a vertical line that goes through the vertex of each of these parabolas. The equation of the axis of symmetry for the parabola on the left Well, the x-coordinate of all the points on that axis of symmetry is 0, so its equation is x equals 0. And the equation of this axis of symmetry, notice the x-coordinate of all the points on the axis of symmetry is 2. So its equation, x equals 2. And that's the end of the Intro to Quadratics lesson. Go ahead and go to Jensen Math, get the free worksheet that goes along with this, and give it a try so you get comfortable working with quadratic relationships.
Jensen Math.